grateful to the organizers for the really nice meeting, and it's a pleasure to be back in Cape Town another time. So in this talk I will describe an application of dissipative effects in the perturbations of dark matter. This is based on a work with two collaborators that some of you know already in UK and Durban, and Anslin at the National Institute of Theoretical Physics in Stellenbosch. So I will briefly start with the usual introduction. I'm sorry for the redundancy that is inevitable in these cases. I will talk briefly about background cosmology and growth of perturbations. And then I will move on to describe some models of bulk viscosity, in particular the causal theory of viscosity that I'm going to use in describing viscous dark matter, its evolution, the evolution of its perturbations. Then I will give some conclusion and possible outlook of the work. So in this donut chart, we have the usual representation of the components of the universe at present time. We are here, we are 4%, less than 4%. And most of the energy content of the universe is dark energy. And the other great component is the cold dark matter. This is in the framework of lambda CDM. So I will talk about a small modification of the lambda CDM paradigm. So as we know, dark energy is introduced in the model in order to describe the accelerated expansion of the universe, while dark matter drives the formation of the large-scale structures that we observe in the universe. So in the context of the lambda CDM model, cold dark matter is described simply as a pressureless perfect fluid. Its dynamics is essentially clustering under its own gravitational pull, and the resulting gravitational wells are the seeds of the formation of the structures of baryonic matter that we observe. So lambda CDM reproduces at the background and perturbative level most of the observational features. Now, I'm not an expert on n-body simulations, but that's why collaborations are useful. And in n-body simulations, we have actually a problem, which is the prediction of too much clustering. I can name two of these problems. For example, the simulations predict too many low-mass satellite galaxies around the Milky Way, and the halo density profiles of dwarf galaxies are too crispy in the center. And the feature of this problem, common feature, is that this excess of clustering mostly regards low redshifts. So there have been some proposals in order to fix these problems. For example, baryonic feedback on the formation of, on the collapse of cold dark matter, warm dark matter, which relaxes the assumption of pressureless feature, obviously modified theories of gravity, and this is the point I will describe in the following, which is dissipative effects in the cold dark matter fluid, which is in some way similar to the warm dark matter approach, we will see. So we will consider background cosmology and isotropic homogeneous expanding universe, which is described by the Hubble function. And in it, the fluids living in the background cosmology will be described by an energy density ρ and an equilibrium pressure P. Obviously, one has to provide an equation of state relating the pressure and the energy density. Through the definition of the equilibrium pressure, one can define the adiabatic speed of sound of the fluid. And it's possible to show that from the conservation, from the total conservation, the fluid expands adiabatically, that is, the entropy of the fluid doesn't change. At the perturbative level, one usually at first order in perturbation splits the energy density into a background contribution and a perturbation, and is usually better to consider the density contrast, which is the ratio between the two components. If one considers situations within the Hubble radius and in a linear regime, the Newtonian theory of perturbation is quite good approximation. So the density contrast will evolve according to basic fluid dynamics. And putting together the equations, one can arrive at a second order equation, evolution equation for the density contrast, which is similar to a damped harmonic oscillator. One can see that the appearance of the adiabatic speed of sound here, so that for a pressureless dust, this contribution vanishes and there is no scale dependence in the evolution. So if one considers deviations from thermodynamical equilibrium in the fluids, it means that one considers dissipative effects in the fluids. In general, among the different dissipative effects in a Friedman-Robertson or Walker background, the only contribution that is relevant is bulk viscosity, and it acts as a modification, a scalar modification to the equilibrium pressure. It can be regarded as a phenomenological effect of non-adiabatic expansion of the fluid or friction between two different species of fluids. In the 40s was proposed the first order theory for dissipative effects by Eckert, which relates the bulk viscous pressure to the expansion of the background metric. I will skip this. The effect of the expansion on the pressure of the fluid, it will be such that it will lower the total pressure, the effective pressure. This is a non-causal theory, and it's possible to show that it's unstable and pressure perturbation travel at infinite speed. So in the 70s, and by the end of the 70s, a causal theory was proposed, which considers second-order deviation from equilibrium. The expression for the bulk viscous pressure is not anymore direct relation with the expansion, but is actually a transport equation, a dynamical equation that introduces a relaxation time into the dynamics. This relaxation time tau is related to the so-called dissipative sound speed, so that the total sound speed of the fluid is given by both the adiabatic and the dissipative contributions. So what we are considering in this work is the usual isotropic and homogeneous background cosmology. The fluids that are living in it are cold dark matter and radiation and lambda, the cosmological constant. And the modification in the dark sector regards the dark matter, which will be characterized by a vanishing equilibrium pressure, like in the lambda CDM model, but with an additional viscous dissipative contribution, so that the total pressure of the fluid is determined by the viscous bulk pressure. Moreover, this viscous bulk pressure will evolve following the Israel-Stewart causal theory, and we specify the form of bulk viscosity. This is a usual choice, mostly phenomenological choice in the literature. It's a power of the energy density of the fluid, so that in the end the observational parameters that we need are the Hubble parameter and the densities of the species involved, and the free parameters are this zeta naught, the exponent s, and the dissipative sound speeds. So by applying Newtonian perturbation theory to this model, one can show that in the end the evolution of the density contrast takes this form. I'm not writing the whole, equation because it's too long, but I'm highlighting the contribution that comes from the inclusion of the causality in the dissipative processes, and which is described by this dissipative time tau. Obviously, when tau goes to 0, one recovers the Eckert non-causal viscosity description, and zeta tending to 0 instead recovers the standard lambda CDM model. So we notice that the appearance of the tau, the dissipative time, comes into combination, or only in combination with the expansion h, which means that we can analyze this as a ratio between time scales, in particular relaxation time over time of the expansion. So in a single fluid model, this ratio between times is proportional to the scale factor to the power, to a certain power. And one can show that at early times, when a tends to 0, we have, depending on the value of the exponent s, two different behaviors. So when s is less than 1/2, at early times the ratio is, the contribution coming from causality is negligible. And the modification due to causality can show up only at later times. This, I note that the dividing value as 1/2 is, has been shown many times in the literature, but at the background level, and it's related to the early or late occurrence of accelerated expansion due to viscosity. But here we just regarded the perturbative level. So in these plots, I'm showing the numerical results for the evolution of the density contrast as a function of the scale factor for the case of s less than 1/2. So we can see that at early times we don't have any, all the models are behave in the same way. The dotted line is the lambda CDM model, while the dashed line is the non-causal Eckert model. These, the color plots are corresponding to the causal description of dissipative processes for different values of the dissipative sound speed. One can see that the introduction of the dissipative causal processes can actually interpolate between the non-causal theory and the lambda CDM. On the right-hand side, I'm showing also the growth factor, which shows that the modification of the growth factor, one can have modifications of the growth factor at low redshifts due to the causal inclusion of causal dissipative processes. So I'm showing other plots which show the same trend but at different scales, for example at galaxy scale. And I show also the case when s is greater than 1/2, which instead leads to an enhancement of the growth of perturbation. So in conclusion, if one considers a causal theory, Israel-Stewart's causal theory of dissipation, with a specific range of the exponents of the bulk viscosity, one can show that this model can lead to suppression of clustering at late times of low redshifts, whereas with the complementary choice of the exponent, the general trend is an enhancement of the clustering. An interesting feature that I'm not showing here because of time is the Jeans mechanism modification, because in this case we have a third order evolution equation for the density perturbation, which would mean that we have more than two regimes. We could have more than two regimes in the Jeans mechanism. And work in progress that is now underway is the relativistic perturbation, analysis of the relativistic perturbations, including the causal effects of dissipation. Also because the causal theory of viscosity would fit well in a relativistic context. So thank you.
Giovanni, so with viscous fluid, you typically have a small scale, a minimum scale, right? Okay. So what's this scale in solar masses in your model?
What do you mean by minimum scale?
So you cannot create structure below a certain mass.
Yes.
So you take the A or solar masses. Question, have you worked out what is this scale in your model?
No, but that would be also related to the issue of the genes mechanism. We haven't yet worked out the full.
I understand you want to resolve the substructure problem.
Yes.
We do observe objects.
Yes.
That have thousands of solar masses.
Yes. Yes.
And they are there.
But I don't have yet an answer to this.
I'm troubled by the use of some of the terminology, equilibrium and viscosity, since at a basic level, you're dealing with a collisionless Boltzmann equation. There are no hard collisions, unless you have some of your primordial black holes that can have hard collisions. But let's assume not. Conventional particle matter is not going to relax. Therefore, it's more like a situation which you commonly encounter in plasma physics, right? Where you know that it's the collisionless Boltzmann equation, it's a proper description of a dilute plasma, but at the same time, for pragmatic reasons, you use hydrodynamics, magnetohydrodynamics, to get a rough idea, but with the knowledge that it's not really what's going on. And I'm just suggesting that it may be the same thing. You may get some of the sense of the phenomenology right, but the physics underlying the idea that there's an actual viscosity here may be misleading.
So it's more like a phenomenological description instead of what really happens. It could be, yes.
And the other aspect of that is, of course, the violent relaxation. If you combine violent relaxation with just general argument that any system that is complicated enough will approach something that looks like a thermal distribution. And you see the same thing in heavy ion collisions. You don't have to, when heavy ion collisions, you know that the collision time is too short for there to be thermodynamic equilibrium. Yet fits to the particle spectra look exactly like thermal equilibrium because it's all fake in a sense.
Just one comment.
Yes.
So, if I understand correctly, what you said, you model this bound viscosity essentially as a contribution to the isotropic pressure, right?
Yes.
So we know that anisotropic pressures have the same kind of, they're more general, of course, but have the same kind of thing. And an interesting parallel with what you're trying to do is with some form of modification of gravity, because they also present non-trivial anisotropic pressure.
Yeah.
So the fact that you have, for example, this effect on the genes mechanism, which is of higher order, it's very similar. I don't want to say the same because it's there are profound physical differences. What happens, for example, in the contribution of gravity? So in there you have a curvature-induced anisotropic pressure, and it does almost the same thing that you're doing. So you might want to use that when you do the relativistic perturbations as a guide to what you might find, or vice versa.
Okay. Thanks.
Yes. So, what about the effect on the background? Suppose you have a model for some values of S and some values of tau, so that you reproduce the right properties of structure formation and possible scales. Is it going to spoil background?
No, actually, yeah. In this case, the modifications that we considered and that give rise to this, for example, to this kind of modification of data, these do not affect touch the background.
They don't touch the background at all?
No, the effect is too low.
Okay,
The
so-
parameters are such that the background is not affected.
Other questions or comments? Let's thank Giovanni again.